Hi everyone, my name is Pavitra V, Department of Chemistry. Today we are going to discuss a topic called carbon nanotubes. These topics come under nanotechnology, in which it is the study of nanomaterials which is having a size varies in nanoscale. So nowadays we have so many applications of nanotechnology in various fields. In that, one of the topic is carbon nanotubes. First, we will discuss the definition of carbon nanotubes. They are of tubical shaped materials made up of carbon having a diameter measuring in a nanoscale or a nanometer scale. Carbon nanometers are formed from essentially the graphite sheet, and the graphite layer appears somewhat like a rolled up continuous unbroken hexagonal mesh. So it looks like a mesh which is continuously rolled up, and a carbon molecules at the apex of the hexagons. Nanotubes are the members of the fullerene structures or the families. So fullerenes are nothing but they are the clusters of carbon atoms. It is also an allotrope of carbon. Their name is derived from their long hollow structure within the walls formed by one atom thick sheets of carbon. So it is also called as graphenes. You can see in the figures or in the images, this ball-like structure is nothing but fullerenes, and this tubical structure is our carbon nanotubes. And next we will move to the classification or the types of carbon nanotubes, in which they are mainly classified into two types: single-walled nanotubes and multi-walled nanotubes. Other than this, we have torus, nanobud, graphinated carbon nanotubes, nitrogen-doped carbon nanotubes, p-pod, cup-stacked carbon nanotubes. We will see one by one in that. First one is the single-walled nanotubes, which is having the diameter 1 nanometer, so which is having a band gap 0 to 2 electron volt. So we know that in the conductors, insulators and in semiconductors, we have valence band and conduction band. The electrons present in valence band are not capable of conducting electricity, whereas the electrons in the conduction band will conduct electricity. There is a difference or the gap between valence band and the conduction band, that is our band gap. If the band gap is more than 2 electron volt, then it is considered as insulators. Whereas the band gap is 0 to 2 volts, then it is called as semiconductors. Whereas the band gap is 0 or the valence band and conduction band are merged, then they are called as conductors. So this is actually a semiconductor or a conductor. They are the good conductors of electricity. A one atom thick layer of graphene into seamless cylinder. Seamless is nothing but there is no joints. There is no joints in the cylinder structure. Their electrical conductivity can show metallic or semiconducting behavior, as we have band gap 0 to 2 electron volt. So after that we will move to the multi-walled nanotubes. In multi-walled nanotubes consists of a multiple rolled layers of graphene, which is having an interlayer distance 3.4 angstrom. Angstrom is nothing but 10 power minus 10 meters. To describe the structure of multi-walled nanotubes, there are two models. First one is Russian doll model and the second one is parchment model. You can see this image. In the parchment model, it is continuously rolled up, whereas in Russian doll model, we will see a concentric circles like rolled up. So this is the two types of models in multi-walled nanotubes. Other classifications are torus, which is a donut shape. See, you can see in the image, this is a carbon nanotube bent in a torus shape, which looks like a donut. And the next one is the nanobud. Here actually a carbon nanobud is nothing but which is created by combining a carbon nanotube and a fullerene structure. This spherical structure is called fullerene, which looks like a bud in the tree or in a plant. So hence it is named as nanobud. And after that we have a graphinated carbon nanotubes. They are new hybrids that combines graphitic foliates. Foliates are nothing but leaf-like structures grown along the side walls of this nanotubes, multi-walled nanotubes, which looks like a leaf projected in a plant. Next one is the nitrogen doped carbon nanotubes. Doping is nothing but addition of some impurities. Here the doping agent is nitrogen. We are doping a nitrogen into a carbon nanotubes in order to enhance the storage capacity of lithium ion batteries. For example, we are taking a lithium ion batteries. Nitrogen doping provides defects in the walls of CNT carbon nanotubes, allowing for lithium ions to diffuse into interwall space. So this is the application of N-doped carbon nanotubes. And then one is p-pod. P-pod is nothing but the carbon p-pod is a novel hybrid carbon material which traps fullerenes inside a carbon nanotube. So you can see in the image, this green color nanotube is having a light colored fullerene structures or a football like structures inside that nanotubes. When you open this, you will see like a pea-pod structure. Next one is the cup stacked carbon nanotubes. Here it exhibits the semiconducting behavior due to the stacking or the arrangement of microstructure graphene layers. So which looks like a cup which is placed one above the other. This is the cup stacked carbon nanotubes. Next one, we will move to the properties of carbon nanotubes. About the strength, carbon nanotubes are the strongest, flexible and stiffest materials yet discovered in terms of tensile strength, that is the stretching, and elastic modulus respectively, which is having a high elasticity. And next come to the hardness. Hardness is up to 152 gigapascals. So it is very high hardness, and the bulk modulus is about 462 to 546 gigapascals. And of carbon nanotubes are greater than diamond. It is more harder than a diamond, which is considered the hardest material. Next come to the electrical properties. Because of the symmetry and unique electronic structures of graphene, it acts as a good electric conductor. Next one is the thermal conductivity. All nanotubes are expected to be a very good thermal conductors along the tube. Next one is electromagnetic wave absorption. There has been some research on filling multi-walled nanotubes with the metals such as iron, nickel, cobalt, etc. to increase the absorption effectiveness of multi-walled nanotubes in the microwave region. So in electromagnetic radiation we have so many regions. In that we are using the microwave region. So you can see this microwave in your microwave ovens. So we have so many applications regarding this microwave region. In order to increase the absorption capacity, we are inserting this multi-walled nanotubes with the elements such as iron, nickel and cobalt. Next one is the thermal properties. All nanotubes are expected to be a very good thermal conductors along with the tubes, but good insulator laterally to the tube axis. So this is the some of the properties of carbon nanotubes. Next we will move to the synthesis of carbon nanotubes. We have three methods. First one is arc discharge method. So this is the image which explains the arc discharge method, which is having two electrodes. One is anode and another one is cathode. This is the cathode deposit area. These are the nanotubes produced between the anodes and cathode. This apparatus is placed inside a chamber which is filled with a helium, that is inert gas. There will be no influence of other oxygen or the other atmospheric gases. There will be a production of arc in between two electrodes. From that arc there will be a production of nanotubes. So this is the apparatus setup for arc discharge method. Next one is the laser ablation method. It was developed in the year 1995. So this is the apparatus setup for laser ablation method, in which this chamber is also filled with an argon gas, that is an inert gas, in order to avoid the abnormal reactions inside this furnace. So this furnace is maintained at a temperature of 1200 degrees Celsius, and this is the graphite which is a target. From this a carbon nanotube is produced. So this is a anti-arc laser, which is actually a crystal used to produce a laser, and this is the nanotubes which are produced due to this process or the phenomena, and these nanotubes are cooled and collected in a cooler edge. So this is the apparatus setup for laser ablation method. And the third method for the preparation of carbon nanotube is chemical vapor deposition method. So this is an important three phenomena which explains the production of carbon nanotubes. In chemical vapor deposition, this is the apparatus setup. In this apparatus there will be a quartz tube. In the quartz tube there is a gas inlet and the gas outlet. We are using a gas C2H2N2, and this is the inlet for the gas. This is the quartz board. We are using a quartz material because it can withstand to a very high temperature. Hence we are using a quartz material, and this apparatus is kept in between a oven, inside a oven which is maintained at 720 degrees Celsius, and a sample is placed on the quartz board. So when the temperature is raised from this sample or the graphite, there will be a production of carbon nanotubes. That carbon nanotubes are carried with this gas, and using a gas outlet it is collected over a other chamber. These three are the methods used for the production of carbon nanotubes. When we move to the applications of carbon nanotubes, there will be a large and enormous applications of this carbon nanotubes, and carbon nanotube members for transdermal drug delivery. As it is having a tubical structure, the drugs can be introduced into a body through that tube. CNTs for cancer treatment. In the cancer treatment also we are using this carbon nanotubes, and cardiac autonomic regulations, platelet activation, tissue regeneration, and finally the first point is repeated, carbon nanotubes in drug delivery. And these are some of the applications of carbon nanotubes in the medical field.